So if my events are disjoint, the probability that they both happen is 0. Okay? But let's look at some non-zero ones. So new probability rule concept here. If the probability of A, I'm going to write and B, if I can type, is equal to the probability of A times the probability of B, events A and B are called independent. Okay. If not, then they are dependent events. Okay, so conceptually what independence means. So two events are independent. Sorry. If knowledge of one event happening no. If not, then there's two event. Oh, thank you. Two. Sorry. Okay. If knowledge of one event happening does not change the chance of the other event happening. What? Okay. Okay. So let me pose some questions to you about things that may or may not be independent. Okay. I'm going to flip a coin. I flipped a coin and I get heads. I know one event that happened. I got heads. I flip that coin again. Does getting heads on that first coin change the chance of getting heads on the second flip? No. So those two events are independent. So we'll list some independent events here. Maybe you can think of some. So dice and coins are independent. Can you think of any other events that might be independent besides dice and coins? Random number generator. I can't spell. There we go. Okay. All right, so cards, it depends upon whether you replace. Okay, so we'll do that when we get to dependent. Okay, so I'm going to give you an example of how to handle a problem where things seem to be independent. Okay, so let's suppose that 90% of students at our school, suppose, jeez, I need to type, I think. Okay. This is going to be like the homework problem from the other day. 90% of the students at our school are in favor of abolishing exams. Do you think that's about true? Think it might be a little closer to 95? Maybe 99? Maybe 99.9? Okay. All right. All right, you're going to ask 4 students independently of each other. How could I ask them independently of each other? I'm not going to walk up to 4 students all standing together and ask them this question, because the answer by the first student may change what the second student thinks. So instead, I ask one student over here and another student over there, another student over there, another student over there. So they're independent. Maybe I get a random sample of students somehow. Okay. So I have independence here. So let's see if we can figure out what is the probability that all 4 say yes, they are in favor of abolishing exams. All 4 of them give me a yes answer when I ask them this question. So since I have independence, I get to use this thing that the probability of event A times the probability of event B is the probability of event A and B, and I get to carry this out for all 4 students. So the probability of 4 students saying yes will be the probability the first student says yes times the second student says yes times the third student says yes times the fourth student says yes, better known as 0.9 to the 5th power, which is 4, thank you. God. All right. Which is 0.6561. Okay. Now let's do something a little harder. Let's see if we can find the probability that at least 1 says no. Okay. So let's think about this. All right, I could either have, and I'll write down the list again because you like it when I write down the list. They could all say yes. Or I could have 3 yeses and a no. Oops, no, yes, yes, yes. Okay? Okay? So let's see why the complement rule works, because you're going to apply a complement rule here for me. All right, or then I could have 2 yeses and 2 nos. Yes, yes, no, no. No, no, yes, 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 no, yes, no, no, yes, no, yes, no, yes, yes, no, yes, no, no, yes. I get them all? Okay. Or I could have 3 no's and a yes. 1, 2, 3, 4, 5, 6. Got all those. No, yes, no, no, yes, no, 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 no. Okay, that's all of them. That's all 16. No, 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 no. All right. All right, I want at least 1 saying no. That is all of these except the very first one, except all of them saying yes. Okay, so at least 1 no is the complement of all 4 saying yes. So we're going to use the little complement rule that we did a little bit ago, that I gave you a little. So the probability of at least 1 says no is the probability of the complement of 4 yeses. So I'll say 4 yes complement. So that's 1 minus the probability of 4 yeses, which happens to be 0.3439.